Thank you. Thank you very much, Chandra, for my favorite kind of introduction. Thank you all for coming this morning, and my sincere apologies for the gorgeous weather. My initial reaction to the email that Chandra sent me, inviting me to give this plenary talk, was one of complete panic. And it read something like this: "We are hoping that you would speak about classical information theoretic problems, your insights on the important problems that need to be tackled." Now, fortunately, when I read emails, I rarely read beyond the third line, so I never really noticed the part about the problems having to be important or worthy of tackling, so let's just take that part out. And I needed to further limit the scope of this. So the first thing I decided was actually to speak only about the single user channel. I apologize for that. There are many interesting problems in multi-terminal information theory. It's just that, you know, we have a limited amount of time and I couldn't go into that. I also added selected, just to protect myself legally. And more seriously is the issue of discrete time. The problems that I will talk about are all in discrete time. And it kind of pains me to limit myself to discrete time because I think that there are some really interesting problems in continuous time. But again, we're limited in time and we just couldn't do more than that in this 50-minute talk. These are problems that I've thought about recently. So somehow they've been on my mind in the last few years, so they're not exhaustive by any stretch and they don't give any historical perspective. And the important thing is that these are problems that I actually believe are solvable. And when I look around me and I look at the brain power sitting here, I'm convinced that they're actually solvable, or at least some of them. So I will not ask you to calculate the zero error capacity of a channel or do anything of that nature. Okay, so without further ado, let's introduce the main characters in this plot. The channels that I will speak about are the classical discrete memoryless channel. We have the input alphabet X, the output alphabet Y. The channel law is W of Y given X. And I will only talk about memoryless channels. And I like to define them or to explain them in terms of the output Y being a deterministic function of the input and some source of randomness. You can call it noise or you can call it source of randomness, whatever you like. In some sense, this is what people refer to as the functional representation lemma. But it's just another way of saying that it's a discrete memoryless channel. The only variation on this that I will discuss is the state-dependent discrete memoryless channel. This is a case where we also have a state entering the channel and influencing its output. So now we have a state alphabet S. The channel law is now W of Y given X and the state S. And again, with this functional representation lemma, describing the fact that the channel is memoryless, Y is a deterministic function of the input, the state, and the noise or source of randomness. Now, typically we talk about Shannon capacity, but in this talk I'd like to describe a number of different capacities. So let me go quickly through the kind of capacities that I will discuss. But before that, a few words about encoders and feedback. So this is the classical setup that we love so much in information theory. We have a message set M. We use the channel n times to communicate a message. The rate is 1 over n log of the cardinality of M. I'm using hash for the cardinality of a set. And when we don't have feedback, then the encoder is just a mapping that maps messages into n tuples, or to the n channel uses that are used in order to convey them. And x of m is the result, the n tuple that results when we transmit M. When we have feedback, then things are a little bit more complicated. Now what we send at a given time depends not only on the message, but also on the previously received outputs. So we have n mappings F1 through Fn, and the transmitted sequence X of M is the first component is the result of applying F1 to the message. The second component is the result of applying the second function to the message and what was received in the first channel use, etc. The decoders we will describe are a little bit different from the classical one. Usually when we describe a decoder, it's a mapping from channel outputs or n tuples of channel outputs to the message sets. And the idea is that this is our guess, phi of y is our guess. Here I want to allow a question mark. And a question mark means that what we have is an erasure. In other words, the decoder shrugs and says, I don't know. So success is, of course, defined if the decoder makes a commitment. In other words, it does not erase, does not declare an erasure, and the commitment is correct, or the guess is correct, and phi of y is equal to m. And now we have two failure modes. One failure mode is when the decoder declares an erasure. And the other one is when the decoder actually commits and makes a guess, but the guess is wrong. So these are the two kind of errors that we're going to be dealing with, erasures and errors. Now, the Shannon capacity actually doesn't differentiate between erasures and errors, and it's the highest rate at which we can communicate reliably if we insist that the probability of an error plus the or an erasure will be smaller than epsilon for every message. Or in other words, the probability of success will be at least 1 minus epsilon for every message. So we're allowing both errors and erasures. And what Shannon showed is that the capacity is the maximum of the mutual information between x and y. He also studied the case where there's feedback. And throughout this talk, when I allow feedback, I will put the subscript FB for feedback. So CFB is the capacity with feedback. And what Shannon showed in his 1956 paper is that the capacity is not increased of a discrete memberless channel when we have feedback. And this is probably what this paper is most famous for, but there's a lot more in this paper. And I will be coming back to this paper a lot in this talk, because there's really a lot of wisdom and interesting ideas in there. In that paper, he also defined the zero error capacity. And when we talk about the zero error capacity, we allow neither erasures nor errors. We insist on commitment and that the guess will be correct with probability 1. And again, this is a concept that he introduced in 1956. It gives rise to a different capacity, different number. And again, this feedback is denoted when we have a subscript of FB. Perhaps less well known is the notion of the erasures-only capacity. And in the erasures-only capacity, we do not allow any errors, but we do allow erasures. So provided, of course, that they occur infrequently. So what that means is that if the decoder makes a commitment to a guess, it has to be correct. But it is allowed to shrug and say, I don't know, provided that this happens infrequently. These notions of capacity can actually be described under one setting if you use the notion of lists. And if we denote by, what we do is we look at the observed sequence and we look at all the code words that are compatible with it. In other words, all the code words that have a posteriori probability which is positive, or if you like, all those that with positive probability can produce this output. And we define L to be the number of code words that could have produced this observed sequence. Then when we talk about the zero error capacity, what we insist on is that the probability that the list will be of size bigger than 1 be equal to 0. Because when the list is bigger to 1, we're not sure what was actually sent. And we want to make sure that this never happens. In the erasures-only setting, we want the probability that the length of this list is larger than 1 to be smaller than epsilon. Because whenever this list is longer than 1, we have to declare an erasure to make sure that we don't make an error. There's a final notion of capacity, which I haven't described yet. This generalizes this. This is the notion of the list size capacity. And this is what happens when you insist that the Roth moment of L be smaller than 1 plus epsilon. So it's be arbitrarily close to 1. And rho is a parameter, a positive parameter. One last thing that I'd like to mention here is the notion of mismatch decoding. This is something very close to my heart because this is something that I worked on in my PhD days. So here we have a channel, W of y given x, discrete memoryless channel, and we have a decoding metric, which maps pairs of inputs and outputs to positive, non-negative numbers, and we extend it additively to sequences. The encoder is, as we've seen before, there's nothing new here, but the decoder now is constrained. The decoder must produce the message that accumulates the least metric. So this is how we define it. So this is a requirement that is made. And now we look at the highest rate at which we can communicate reliably over this given channel with this decoding metric. And we denote that by C of W and D, because it's a function both of the true channel W and of the decoding metric D. And again, when we have feedback, we can also study this quantity. And we just didn't put a subscript of FP. OK, so going back to Shannon's 1956 paper, I promised that I would come back to it, and I will in a number of occasions. He didn't just show that the capacity is not increased with feedback. He also argued, and perhaps you could say conjectured, that computing the zero-error capacity is a difficult problem. In fact, he wrote, no method has been found for determining C0 for the general discrete channel, and this we propose as an interesting unsolved problem in coding theory. And in some sense, thanks to this sentence and the attempts that have been made to solve this problem, this has become a benchmark for difficulty in information theory. And let me just give you an example of two kinds of results of this nature. The first is Al-Suede's result about the arbitrarily varying channel. So Al-Suede showed that if you look at the capacity of the arbitrarily varying channel under the maximal probability of error criterion, then solving for it is at least as difficult as solving for the zero-error capacity of a general discrete memberless channel. Another example is a paper by Cizar and Narayan, where they showed that the mismatch capacity is also a very difficult problem in the sense that if you could solve it for every channel W and every decoding metric D, then you would also know how to solve the zero-error capacity of a graph or of a channel. Let me just very, very briefly mention the idea behind Cizar and Narayan's paper, or at least this result in that paper. That paper has a lot of other good stuff. The idea is the following. You want to somehow find, you have a given channel W for which you want to calculate the zero-error capacity. What they suggest is to design a new channel, W prime, different from the original channel. Has very little to do with it at first sight. And they propose a decoding metric. Now, the channel W prime is actually noiseless. It's the most boring kind of channel you can think of. The input is X, the output is going to be X. That's it, there's no noise. But the decoding metric is very clever. It's the metric between X and X prime is 0 if X prime is equal to X or if is confusable under the conditions of the channel. And otherwise, it's something positive. And they showed that if you actually study this mismatch capacity, it's equivalent to the zero-error capacity of the channel W. And this is how this is proved. So I come here to my first problem. I'm going to have about 5 exercises that I propose. The first one is, I'm asking whether computing the erasures-only capacity is at least as difficult as computing the zero-error capacity. So far, we don't have an expression for the erasures-only capacity. Is it because we haven't worked hard on it enough, or is it because it's really a hard problem? I would like to conjecture that actually this is a difficult problem, that it's at least as difficult as computing the zero-error capacity. And I'd like to give you some idea of why this is my conjecture. And it's related to the relationship that has been recently established between the erasures-only capacity and what is called the Sperner capacity of a graph. For this, you need a notion of something which is called the epsilon noise channel, or almost noiseless channel. And this is the kind of channel where the output contains the input alphabet. And the probability that you will receive X if you send an X is very close to 1. So it's larger than 1 minus epsilon. So if epsilon is actually equal to 0, it means that there's no noise. You send X, you get X. Here, the requirement is that it's almost noise-free. So there is a certain probability of epsilon that it will not be X, but it's very, very small. Now, you can define a directed graph. I won't go into all the details related to a given channel. Basically, it's the edge set comprises all the ordered pairs for which the W of y given X is positive. And then it turns out that there's a very beautiful relationship between the limiting behavior of the erasures-only capacity for almost noise-free channels and the Sperner capacity that we've just defined. And basically what it says is in the limit, as the almost noiseless channel becomes noiseless, its erasures-only capacity tends to the Sperner capacity of the underlying graph. Now with this result, we can do something interesting. Because we know that calculating the Sperner capacity is at least as hard as calculating the zero-error capacity of a channel. This is a classical result of Gargano, Kerner, and Vaccaro. And now, the reason why I conjecture that it's a difficult problem is because we conceive that computing the limit of the erasures-only capacity as the channel becomes less and less noisy is very difficult. So maybe, if it's very difficult to calculate a limit, it's also difficult to calculate any term in the sequence. But this is just a conjecture. This is exercise 1 for you to sort out. Okay, so let's go back to Shannon's 1956 paper. By the way, you may have noticed this is probably my favorite paper of Shannon's. He actually realized that computing the zero-error capacity is difficult, but to characterize whether it's positive or not is not so difficult, and he actually managed to do that. So in some sense, it's a poor man's calculation of the zero-error capacity. Okay? He just at least wanted to know whether it's positive or not. And he did. And the result is that although we don't know the zero-error capacity, we have a very simple characterization of when it is positive. It's positive if and only if you can find two inputs, x and x prime, that basically will allow you to send a bit error-free. So every output that is reachable from x is not reachable from x prime, and vice versa. So this is a complete characterization of when it is positive. So the question is, for the other kinds of channel capacities, can we also find something so nice, saying we don't know how to calculate them, but let's see whether they're positive or not? And the answer is, for example, yes. So the erasures-only capacity, we don't know. And in fact, I conjectured that it was a difficult quantity to calculate, but it's pretty straightforward to figure out whether it's positive or not. What you need is two inputs, x and x prime, and a output, not all outputs, but a particular output that is reachable from one and not the other. Similar question can be asked about the arbitrarily varying channel under the maximal probability of error. Al-Suede told us that it's a difficult problem, but Kiefer and Wolfowitz actually have a complete characterization of the conditions under which it is positive. It has to do with the convex hull of the output distributions that can be induced by choosing different states by an adversary. What about the arbitrarily varying channel under the average probability of error criterion? Here again, we actually have a complete characterization thanks to Eriksson and the Cizar-Narayan duo. Basically, the result is that the AVC's capacity is 0 if and only if the channel is what is called symmetrizable. Symmetrizable just means that you can find a conditional distribution on the state given the input that will result in all the outputs having the same conditional log given the different inputs. It's a little bit, it's a little bit a mouthful to say, but the formula is actually right there on the screen, and it's pretty straightforward. It's pretty obvious that one direction, that is, that if it's symmetrizable, then the AVC capacity is 0. Much harder is the other direction. This is a result, as I mentioned, of Cizar and Narayan. I should probably tell you something about this duo. They are very kind people, very soft-spoken, very nice to interact with. But when they go after a problem, and when they, it can be, here's what happens. Okay, so you have on the left Imre Cizar and Prakash Narayan on the right, and in the middle you'll see the last problem they took a stab at. So. Okay, and speaking of these two guys, we can ask, again, we don't know how to calculate the mismatch capacity. Can we find out whether it's positive or not? And they characterized the conditions under which it is. I probably have to say something about this characterization. Basically, it's positive if we can find a pair of inputs, x and x prime, for which some quantity that I'll explain in a minute, mu x x prime, is negative. And this mu x x prime is the difference between two expectations. One is with respect to the conditional law under X, and the other is under the conditional law of the channel under X prime. And the intuition is actually pretty straightforward. What you want to think about is that if the input is X, then it should be more likely that the metric will give X a score which is lower than X prime, and therefore you want the first expectation to be negative. And if the input is X prime, then you want the score to go the other way, which would make the second expectation positive, and therefore negative minus positive, you expect this thing to be negative. And indeed, if this difference between two expectations is negative, then the mismatch capacity is positive, and this is an if and only if condition. So I come now to exercise number 2, which is related to the Gelfand-Pinsker problem, or if you like, the state-dependent discrete memoryless channel, when the encoder has non-causal information about the states. And we wanted to understand its behavior with respect to the zero error capacity. And the question is actually now very simple. Can you characterize which discrete memoryless state-dependent channels have positive zero error capacity when the transmitters reveal the state sequence non-causally? And there's no feedback in this story. So it's a simple, quote unquote, simple extension of what Shannon told us, but now when we have states. I should say a few things about what we know about this problem. The lack of feedback is detrimental. So if you have feedback, you can do better than if you don't have feedback. The fact that the site information is non-causal is better than the case where it is causal. Unlike in the zero error capacity, sending one bit may require multiple channel uses. It's not enough to just send X and X prime to convey your bit. And I should also mention that Anina in her Ph.D. thesis actually solved the case where there's feedback. And she has a complete characterization of the Gelfand-Pinsker zero error capacity with feedback. Again, it's one of those cases where actually feedback helps. So how do we usually prove that some non-standard capacity is zero? Because in these characterizations, we always have to show if some condition holds, then we can communicate reliably, and if it doesn't hold, then we cannot. And how do you do cannot? You cannot use Fanos inequality because it has nothing to do with mutual informations. It may have to do with zero error capacity, it may have to do with mismatch decoding, etc. And the idea is actually very simple, and it's been around, and it's all the papers related to these issues. I just want to give it a name, and I want to say that a channel is bit carrying. Basically, if you can send one bit over the channel reliably. So the idea is the following. You want to send one bit. You can choose your block length arbitrarily large, and you want to make sure that by doing so, you can send this single bit reliably. And reliably means, of course, on the problem. So it could be with zero error, if you're interested in zero error capacity. It could be with erasures only, with mismatch decoding, etc. And basically, the idea is very simple. If your capacity is positive, then you should be able to send a bit reliably. And if you cannot even send one bit reliably, then surely you cannot communicate at any positive rate. So the main key is that if you want to show that the capacity is zero, you show that you can't send a single bit, and therefore the capacity is zero. So in some sense, all these results rely on this. It's in all the results that I've mentioned to you. And in some sense, you can strengthen them. If you look at the proof, you realize that basically, if some condition holds, then the capacity is positive. And if it doesn't hold, you can't even send one bit. So this is the main idea. Okay. 1956 paper, Shannon showed that the feedback can actually increase the zero error capacity. In fact, he gives credit to Peter Elias for this. If you look at his paper, he actually says, I'm indebted to Peter Elias for first pointing out that a feedback link could increase the zero error capacity. And this is what he showed. And of course, once you see this, you can start asking about various other notions of capacity, whether feedback actually can increase them. And the answer is that many of them, yes. The trick in proving results of this nature is that for many of them, we don't have an expression. So you want to say that A is larger than B, but you don't know how to calculate A, and sometimes you can't even calculate B. So the idea is usually to find some kind of an example for which you can calculate the two quantities and then show that a strict inequality can hold. So this is the example. This is how it's done in the erasures-only capacity, which is increased with feedback. List size capacity, the mismatch capacity also is increased when you have feedback, or can be increased. And the average probability of error, AVC capacity, similarly. Let me just give you quickly a proof of the fact that the mismatch capacity can be increased when you have feedback, because it's so simple and because it's really 3 lines. So we remember from Cesar and Narayan that actually if you choose your decoding metric in a clever way, so 0 if there is a positive probability of going from X to Y, and 1 otherwise, then the mismatch capacity is actually equal to the erasures-only capacity. This is also true when you have feedback. So all you need now is find some channel W for which you know that feedback increases the erasures-only capacity. Let's say that you found one. Then immediately you get this type of result also for the mismatch case, because basically what happens is that the capacity with feedback under mismatch conditions, because of our choice of W and the decoding metric D, is equal to the erasures-only capacity with feedback. Because of our choice of W, this is larger than the erasures-only capacity without feedback, and the erasures-only capacity is again the special case of the mismatch in this setting. This is basically the proof. Okay, now what Shannon also did is he showed that surprisingly, although calculating C0 is very difficult, calculating C0 with feedback is not so difficult. It's actually fairly straightforward. And this is his result. He basically gave a very simple expression for the zero error capacity with feedback. And inspired by this, we can also ask whether perhaps some of the other problems become easier when you have feedback. So one case is the erasures-only capacity. We don't know it without feedback, but we actually do know it with feedback. This is a very simple expression for that. And then there's, you can also ask the same question about the list size capacity. Again, we don't know the list size capacity without feedback. But Christoph Bunte in his PhD thesis showed that if a channel has positive zero error capacity, then he can actually give you an expression for the list size capacity with feedback. And it's very simple. It's just related to Gallagher's E0 function. So if the channel has positive zero error capacity, then the list size problem is solved when you have feedback. And this brings me to exercise number 3, which is, can you calculate the feedback list size capacity when the channel does not have a positive zero error capacity? Or maybe can you prove that it's difficult? I don't know, but this is my question to you. Now, you notice that, okay, to be fair, when I saw this, I was all excited, and I said, look, we don't know how to calculate the mismatch capacity. Maybe I can now calculate the mismatch capacity with feedback. Wouldn't that be cool? And after thinking about it for a short while, I realized that that's not a good idea, and that's not what I want to do. And I'm not going to ask you to do it either, because this is also a very difficult problem. Even though you have feedback, this is still a difficult problem. So the mismatch capacity is difficult both with and without feedback. And the reason is that also with feedback, it's actually as difficult as calculating the zero error capacity. And it's really not difficult to prove this. The idea is actually very simple. We go back to Cesar and Narayan's argument for the case without feedback, and we realized that when they were trying to calculate the zero error capacity of the channel W, they were using an auxiliary channel, which was W prime, which was noiseless. And on a noiseless channel, feedback doesn't help. So actually, with or without feedback, it's all going to be the same. And therefore, this is not exercise number 4. Okay. Can feedback increase the capacity from 0? Okay, so what Shannon actually showed in 1956 is that the zero error capacity is positive with feedback if and only if it is positive without feedback. So feedback can help you, but it cannot increase the capacity from 0. If it was 0 without it, it will be also 0 with feedback. And of course, we can ask the same question about other forms of capacities. And okay, so we know this about the zero error capacity. It's true about the erasures only capacity. It's true about the list size capacity. Again, this is one of the results of Christoph Bunte. And the idea is always the same idea. So basically what you do is if you want to show that also with feedback the capacity is zero, what you show is that even with feedback, you cannot send one bit reliably. This is the idea. There are a couple of examples where this is not the case. I mentioned already the Gelfand-Pinsker problem for the zero error capacity. And it's also not true about the average probability of error AVC capacity, which actually can be increased from zero. Yeah, I'm not sure what I'm pressing. I noticed it too, I hate it, but are you sure it's me? I'm not touching anything now. With my, it's correlated with what? Not moving, okay, but I have to click on something, right? Okay. I'll take the zero error capacity problem any day. Yeah, so I said the AVC actually is increased when you have feedback. This is a result of Al-Suede and Chizar. And their idea is based on the fact that through the feedback link, you can generate common randomness. And the common randomness is then used in order to bring up the channel capacity from zero to something higher. It's still moving. Can this be locked? Why do you? Go ahead and do it now. Okay, so my apologies again. So here's a very simple question that has been bugging me for, about a year. Can feedback actually increase the mismatch capacity from zero? And I think we have to move further. Why don't I just go ahead and okay. My apologies, oh, that one's also has it. Never mind, okay. So the idea I thought was a very simple result. I thought it was going to be like bit carrying issue kind of stuff that you've seen before. And this was supposed to be section 6 in a conference paper that I submitted back in 2016. And the deadline came for actually submitting the camera ready, and I couldn't quite get it right, so I just decided that I'm not going to commit, and there's no answer there for this problem. I was fairly sure that this was straightforward. I was completely naive, and I didn't understand how tricky these things are. So my guess was, yes, if it's zero without feedback, that it's also going to be zero with feedback. And the plan of attack was actually very straightforward. To prove that, what I wanted to do was show that if the mismatch capacity is zero without feedback, then you cannot send a single bit reliably also with feedback. And I failed. And instead of going to a shrink, I'm discussing this with you. And I want to try to explain why, and maybe you can help me out with this. Okay. So we know when the mismatch capacity is zero without feedback. Thank you, Chizar and Ariane. It's when this horrible mu x and x prime is not negative. So we can't find a pair x and x prime that's going to make it negative. So why did I fail? I thought it was going to be a straightforward corollary of these guys. You just copy from the giants and you get the result, and that's it. So let me try to explain what they did and where the difficulty lies. So their idea was, if you want to send one bit without feedback, basically what you're sending is one n-tuple corresponding to h equals 0, and one n-tuple corresponding to h equals 1. And in the locations where under both hypotheses what is being transmitted is the same, you can ignore these locations because that means that the output is going to contribute the same metric to both hypotheses. So it's kind of silly to send the same symbol under both hypotheses because it won't help you differentiate. So you ignore those locations, and then you're left with a whole bunch of other locations. And then you use a central limit theorem to actually study the way the probability of error behaves. In this case, it's a Berriasian version. And if there aren't that many of them and the central limit theorem doesn't really kick in yet, then you use some kind of a simple bound on the tail distribution of a sum. So this was what they did. And I thought that all I needed was a central limit theorem for martingales, because what I send now is allowed to depend also on the past. Now, this is not exactly my strength, so I went to my buddies, Venkat and Alan. They eat these things for breakfast, and they educated me about central limit theorems for martingales. But it turned out that I asked them the wrong question. But I learned from this a lot. I learned about martingales, and I learned that it's better to ask the wrong question of the right people than to ask the right question to the wrong people. And these were definitely the right people. Okay. So there's a twist, and I didn't appreciate that at the time. It's true that when you don't have feedback, sending the same symbol under the two hypotheses is ridiculous. It doesn't help you. But when you do have feedback, there's an interesting phenomenon that occurs. Indeed, it's pointless to do it at the beginning of the block, because this can be ignored. However, it's an amazingly clever way of actually introducing a stopping strategy. So basically what you do is if you want to stop at a certain time t, you're not allowed to do this because we're in a finite block length, we're in a fixed block length regime. You can't just say, now I stop. But what you can do is effectively stop. And the way you do that is by forcing both encoders under the two hypotheses to transmit the same symbol. And that's effectively stopping the whole process. So as of that time t, you just make sure that under both hypotheses, you're sending the same symbols. So what is the issue here, and how can you actually exploit this? Is it possible, maybe, that you cannot send a bit reliably without feedback, but with the feedback in this clever stopping strategy, you will somehow manage to send a bit? And the answer is yes. This kind of completely shocked me. So you can actually have a situation where you cannot send a single bit without feedback, but you can with feedback. And I want to give you this example because it's kind of cool. So this is a binary input, quaternary output. And it's noiseless in the following sense, that if your input is x, the output is a pair x and theta. So you actually see what is being sent. And you see some noise or randomness or whatever it is that you want to call. This is Mr. Theta, and it can be either bad or good. Now, bad or good does not refer to the channel because the channel is fantastic. What you see is what you get. No, what you get is what you send. Okay. So we're assuming here that this theta is IID and that it's equally likely to be good or bad. And what it does is it actually influences the decoder. When theta is good, what the decoder does is actually very reasonable and very plausible. The decoder actually looks at the output, which is x and theta good, and it gives the metric of -1 to the true symbol that actually generated this output. It knows it because it's noiseless. And the bad input that did not generate this output is going to get a +1, and therefore you actually get fantastic performance, right? Okay, so what you wanted was that the true input gets a negative metric and the wrong input gets a positive metric, and everybody's happy. However, if theta is bad, then it does exactly the opposite. It actually gives a good score to the wrong input and a bad score to the correct input. Now, you can actually quickly figure out that you cannot send a bit reliably without feedback over this channel. You just calculate the expectations that I told you about in Shizar and Narayan's paper, and you will see that you cannot send a bit without feedback. But now let's see what happens if we actually try to exploit this kind of technique of introducing a stopping time. And I claim that you can do wonderful things. And basically what you want to do, and this is where the title of the talk comes in, you actually want to let the noise do the work for you. You just sit back, you wait until this noise, the noise being here the theta good and the theta bad, actually causes the situation to be very much in your favor, and then you stop. So how do you actually do it in practice? To send h equals 0, you just send the all 0 sequence. To send h equals 1, you send the all 1 sequence until a certain stopping time. And that time is when the number of good thetas exceeds the number of bad thetas. And when thereafter, you send all 0. In other words, thereafter, under both hypotheses, you're sending 0, which I said was tantamount to a stopping. So basically, we're stopping the moment the number of thetas that are good exceeds the number of thetas that are bad. And what's so great about that? Well, let's just define +1 to be good and -1 to be bad. The stopping time now is the first time that a random walk on the integers exceeds 0. And you can easily see that actually at time t, at this stopping time, the correct hypothesis accumulates the metric -1, and the wrong hypothesis accumulates the metric +1, and the decision is correct. So the only way we can actually get an error is if this stopping time never happens. Okay, so this is basically the situation where you have a symmetric random walk on the integers, and it never hits the positive half. And you can easily show that this decays like 1 over the square root of n, where n is the number of steps of the random walk. So you give me an epsilon, I choose n large enough so that 1 over square root of n is going to be smaller than epsilon, and this scheme actually sends that bit with probability very smaller than epsilon. Okay, exercise number 4. I've now given you an example where a channel cannot carry a bit without feedback, but it can when you have feedback. And I'm asking you to characterize those pairs of channels and decoding metrics for which you can actually carry a bit with feedback. I should say that this scheme that I gave you is very, very kind of symmetric and very, very, very tailored to the situation that I have in mind. There are two really fundamental things about it. One is that whether theta is good or bad is seen by the output, okay? And the other is there's a lot of symmetry. The random walk is symmetric, and the one makes a mistake if and only if the other makes a mistake, and so forth. You can get rid of the second hypothesis if you use heavy machinery from random walks in 2 dimensions. But I couldn't figure out how to get rid of the first requirement. So I have a sufficient condition. This is a pathetic excuse for why I didn't solve exercise number 4 myself. I have a sufficient condition. I don't want to go into the details, but basically what it is about is that this theta, this noise, is computable from y and not from y and the input. So let's skip that. And basically what it is the same kind of scheme, stopping time. You just have to do a heavier analysis in 2 dimensions with a non-symmetric random walk, and et cetera, et cetera. Of course, you can also ask about necessary conditions for the feedback to allow you to send a bit reliably. And here's a necessary condition. Again, I don't think this characterizes, it doesn't solve exercise number 4. And it says that basically the only way you can do this is if you have at least 2 inputs, x and x prime, for which mu x, x prime is negative, smaller or equal than 0. Okay. This is really not surprising. It's a lame excuse. I shouldn't have even been presenting it to you. The idea is that if this mu is positive, then actually when you, during the communication, the metric difference drifts towards the wrong metric. And this cannot be overcome by a random walk. If there's a drift, it will actually go to infinity. That's the idea. It's not very surprising. If you actually want to do the math, I think you use Helmut's dictum. It's just a matter of discipline. You have to sit down, you close your office door for a few weeks, you hit the books, you do Borel-Cantelli, law of large numbers for martingales, you come out and you say, yeah, the intuition is correct. Okay. But a characterization I don't have, I leave that to you. Now, this doesn't really answer my real question. The question that I asked you was, is it possible that the mismatch capacity is positive with feedback, but 0 without feedback? I can already tell you that coming down the pike, this will become an exercise, but I want to say a few words about this. So why have I not answered this? I just told you that it was possible that you wouldn't be able to send a bit reliably without feedback, but that you would be able to do it with feedback. Doesn't this answer the question? The answer is no, this does not answer the question. Because all I showed you was that I can send 1 bit reliably over the channel. I can do a finite number of bits, but if you want a positive rate, you have to have an exponentially increasing number of messages in the block length. And I actually claim that in this example that I gave you, yes, you can send a bit reliably, but you cannot send at any positive rate. I know this sounds crazy, but if there's one sentence from this whole talk that does not end with a question mark that I want you to remember, it's this one over here. And this is what I've highlighted in red. W and D, this pair, is bit carrying with feedback, yet the capacity is 0. And of course, to prove this, you need a converse. You need to actually show that you cannot send any positive rate. And it's a bit tricky. And the reason why it's tricky is, of course, you can't use Fanos because, I mean, the channel is noiseless. All the mutual informations are, sky high. You cannot use anything like, oh, let's do some, instead of pretending that the functional that I get just the feedback, I'll assume that I'm getting the functional representation thetas, and that I don't just get it strictly causally, but I get it causally. All these things don't work, because suddenly the capacity is going to be, again, sky high. And of course, you can't argue, like in all the other kind of problems, that it's not bit carrying, because we know it is bit carrying. So my claim is that it's bit carrying, and yet the capacity is 0. I'll give you just a hint at the converse. It will require too much time to actually go into the details. It's kind of a cool converse, and the reason why it's cool is because you actually have to use the probabilistic method, which we usually use in the direct part. We actually need this in the converse to this problem. And the way we use it is to actually claim that if any positive rate is achievable, then you can find two messages that are, I want to use the word close, but actually close is not the right word. Actually, I want their Hamming distance to be large. This is the other weird thing about this converse. Usually we want to claim that the probability of error is high by saying that there are two code words that are very close. Here what I want to claim is that there are two code words that are very far. And I use the probabilistic method to actually prove that. And once you find these two messages that are actually far in Hamming distance, you prove that these two are, cannot be communicated. This one bit telling you whether it's M1 or M2 cannot be conveyed over the channel. So the idea is that because the Hamming distance is large, they cannot stop too quickly. The stopping trick doesn't work. So it takes a while before they're allowed to stop. And then the law of the central limit theorem kicks in, and with high probability, here you go. The metric difference is actually going to behave like the square root of n. And after that, you cannot compensate for this square root of n simply by looking at your random walk and praying that the noise will get you where you want to go. Square root of n is too much. It just doesn't work. Is that okay? Okay, great. And of course, I mustn't forget, I wanted to ask, to thank Christoph and Robert for many discussions. They've listened to me patiently over weeks and weeks trying to sort out this converse, so thank you. Okay, so my question was, can feedback increase the mismatch capacity from 0? Now you can take this horrible converse and you can extend it, and almost everything goes through, and therefore the answer is almost no. So I wanted to say no. It's not really no, so I thought I'll make it really big, and then I'll put an exclamation mark, but it's still not really a no. There's a certain caveat, and I couldn't get rid of this. I was kind of hoping to sort it out on the flight, and no, I didn't. So there's a minor condition. I don't want to go into the details, but essentially the answer is that the feedback cannot increase unless there's some weird condition that holds, and I have no idea whether it's relevant or not. And this brings me to exercise number 5, as I promised you. Kindly help me get rid of this stupid caveat, or please produce an example of a pair, W and D, for which the mismatch capacity without feedback is 0, and with feedback it is positive. Okay, so I've given you 5 problems. They tend to be very focused. The question is also whether there's some bigger challenge that we can think about. The examples I gave you were all that showing that seemingly different problems in information theory can sometimes be formulated as instances of one another. And this can be very useful to identify problems you don't want to work on. If somebody showed that it's equivalent to the zero error capacity, go away. And that's wonderful. And it's been very useful in all the cases that I've shown. I think there's a bigger challenge that I would like to suggest to you, which is whether we can find deeper connections where we would show that a solution to one difficult problem would provide a solution to another problem, which is not an instance of it. Okay? In these cases, this was just an instance of it. So can we do something like duality theory or some basic results that will tell us, okay, these two problems that are not an instance of each other are essentially equivalent, or one is harder than the other. So if Chandra will solve the broadcast channel, then we will also know what is the Gelfand-Pinsker multiple access channel solution. I don't know. I think this would be something kind of cool because it would allow us to make progress without actually solving any of the problems. Okay, and with that, I'd like to thank you all. The question was, how many of these results actually depend on the feedback being perfect? And what happens if you actually have a noisy feedback link? The results that are pessimistic, of course, will also hold if the feedback is noisy. And the positive ones some of them become very hard. And I think many of these problems are actually open when you have noisy feedback, when you know that without feedback you can actually increase capacity.
Other questions?
Rami, huh? Oh, Michelle.
I mean, this is, I don't know, unfair question maybe, but since you were playing with these problems so much, so I wonder historically, what do you think? Shannon first tried to solve the zero error capacity before 48, and then he realized it's too hard, and then he arrived to the right definition of capacity, or was it the order of the papers?
Okay, I don't need to repeat because you had the microphone. I don't think it's an unfair question. I think it's a great question. I have no idea, but it's a fantastic question. I am guessing that he understood that you don't want to go with zero error capacity before he went with epsilon, because somehow zero error is much more natural than epsilon error. Yeah, so.
So actually, I'm wondering about this last slide. So how did this person save the world?
Okay. It's great to have you here, Michelle.
It was not set up.
This is Stanislav Petrov was an engineer. He was in the Soviet Union. He was an electrical engineer who was in an early warning, commander of an early warning station that was supposed to give an early warning in the 70s and 80s in case the Americans actually fired nuclear missiles at the Soviet Union. Now, this is actually a true story. And one evening, he actually saw on his radar and on his system that the Americans were attacking. So he saw one nuclear missile, and then he saw two. And at some point, it looked like an attack of about 6 or 8 nuclear missiles. And what he had to do was press a button, call his commander and say, the Americans are attacking. They had about 12 minutes time before basically Russia would be annihilated, and they had to respond. And with incredible I don't know. I have no other word. I don't have no words to explain this. He basically decided that this was an erasure, that this was a mistake, and he did not call his superiors. And at some point, he just called and says, "I have a malfunction," and this was the end of it. So this erasure, my God, that was worthy. The answer is ask Prakash.
Amos, the last comment you made about two different problems that don't derive from each other, but a solution to one can inform us about the solution to the other. Are there examples of such problems?
So, I think that in Chisar and Kerner's book, if my memory serves me right, many years ago, they had some basic network that they showed that if they could solve, they could actually solve a number of different networks. I thought this was an amazing line of research. And this is kind of the stuff that I would love to see more of.
Okay.
I think in terms of duality, we have not gotten there. So there are beautiful results that show you the two problems are dual, and they give you some idea of what the solution to one is based on the solution of the other. But they never quite tell you if you solve this one, you'll solve the other. One might be packing and one might be, it never quite works out. But this is, that's the idea that I have.
And the other question had to do with the converse that you brought up. You said, of course, using Fano is not going to help us. But how about some of the single-shot results and the information spectrum-like results? Do they yield anything, or do they also fall short?
I think they all fall short. There's just, in this particular example, the receiver has just too much information. My suspicion is that they won't do the trick. No.
Thanks.
Yeah.
Yes, so, Varun.
You mentioned that the zero error capacity problem is kind of like a benchmark, that you reduce your problem to that and say that this problem is at least as hard as that. Are there actually such classes of, like in computer science theory, you have NP hard problems, you kind of reduce every problem to that. In information theory, are there such other benchmarks, and are there actually classes of hard problems that you can reduce your problem to?
Not to my knowledge, and I would love to see more of this kind of line of research, but I'm not aware of this. Even the results that I mentioned here, I think they mostly work in one direction. So they show that some problems are as difficult as the zero error capacity. I'm not aware of any results going in the other direction, but I'm not 100% sure about that.
Is there a chance that for the simple channel, not the match channel, we know that memoryless channel feedback does not increase capacity because you have single letter expression, and in the mismatch channel, we know that single letters do not work that well, starting from Huey, ending here with Anelia. Could that be the clue why the problem is a little more difficult with those points that you've mentioned?
It's a bit tricky. So, for example, the zero error capacity, we also only have a multi-letter expression, and yet we're perfectly capable of answering and saying that feedback does not increase it from zero. So, I think there's more to it than that, but I'm not sure. Yeah.
Other questions?
You're always looking at the mismatch capacity as something, unsolvable, bad, hard problem. I wonder if for certain Ds, the problem could be simple or solvable. I mean, clearly, if D could be the maximum likelihood, but then it's trivial. But maybe there are other measures of distance, maybe some, like universal kind of looking at the outputs, or a characterizing group of metrics that will make that mismatch capacity problem solvable?
Yeah, it's a great question, and it's bringing me back to my shrink. I think there is something there. So for example, in this ELAT paper that I mentioned, where I failed to show that the mismatch capacity can go above 0, there was a class of channels there for which I could actually calculate the mismatch capacity with feedback precisely. So this was not an issue. Ofer Shayevitz was visiting me, and I thought that maybe the posterior matching approach might give us an answer to a certain class of mismatch decoding rules. It's all, I think, fascinating stuff, but I have nothing to report in terms of success.
One last question before we close the session. Any questions? No. Okay. So at least if the weather turns bad, we know what to do. We have some 5 problems. So let's thank Amos once again for a wonderful lecture.
Thank you. Thank you.